When I first took statistics, there was a handout and it said at the top, "Is statistics hard?" And the first answer on that was no, it's not hard. And there were a few points made in this short little handout that was statistics is more about philosophy than it is about anything else. And then the second point was statistics is backwards, and that it's hard because we don't really appreciate the backward nature of statistics that prevents us from saying or doing a lot of things that we want to do. And so what this means, statistics is backwards, is the following: that the way we do classical statistics is not that we try to prove something. It's that we do the following. So first, we come up with some sort of null hypothesis. H null. And the null hypothesis is, what would we expect to see if something, if some situation was true? And usually the null hypothesis is there's nothing going on. So we might say we have a drug and the drug doesn't do anything relative to a placebo. Or we might say we have two groups of people and these two groups of people are the same. Or we might say there's two populations and no health disparity exists. That's the null hypothesis. And we set this up not as something that we want to prove, but as something that we almost want to knock down, some sort of straw man or straw person. So the second step after you make your null hypothesis is to go out and collect some data, which in statistics, we always sort of assume it's random and perfect and not biased. And when you take epidemiology, you'll learn that, there's a lot of pitfalls there too. But when we go out and collect our data, then we need to summarize it. And we summarize our data with a statistic. Statistic starts with S. It's this idea of what is going on in my sample. A statistic is just a number that summarizes your data. Once you have that number, now you come here. What is the chance of getting my data if the null hypothesis were true? What's the chance of seeing the difference that I get if actually no difference existed in the real world? I know that sounds a little weird, but you're sort of saying, I know there's going to be noise. I know there's going to be randomness. I know things are going to bounce around and things are going to show up. But how weird or how strong of a signal am I getting with my data? So this number 4 is interesting because this is sort of the lay person's definition of a p-value. What's the probability of getting my test statistic if the null hypothesis is true? Now remember, probability can go from 0 to 1. So if that probability is very small, let's say your probability is 0.00001. What's the probability of getting my data if the null hypothesis is true? If that probability is really weird, then either we're really, really lucky or unlucky, or it's really random that occurred, or perhaps that null hypothesis was false and we need to reject the null hypothesis. So when we talked about sampling some athletes and seeing, are they cheaters or not? Well, let's assume that they're not, and then collect some data and then say, wow, if this guy was drug-free, it's really rare we would get a value that high. So what do I do with the null hypothesis? I reject it. And we're going to see this important step here, rejecting or failing to reject the null hypothesis when we compare our p-value to that criterion that we have. If you remember, the criterion for when something is weird or significant, we use the Greek letter alpha. And that's our cutoff for what we're going to see as statistical significance. So when you get lost in this process, and you will, remember that statistics is backward. First, you say, what would I see if nothing was going on? Then I collect some data, and then I say, what's the probability of getting those data if nothing's going on? And if that's small, Tibor, how small? Well, smaller than alpha, then we will reject that null hypothesis. We'll come back to this again, but remember, statistics is not hard. It's backwards.